Okay, so let's unpack this right out of the gate. How do we go from sharks biting underwater internet cables to, like, AI writing code that requires literal mathematical proofs?
It's quite the jump.
Right, and then finally to using advanced cryptography just to verify where your morning coffee came from.
Yeah, the connections are wild.
Because, when you fire up your browser, you get this illusion of absolute perfection. Like you click a button and the internet just delivers.
That magic.
Exactly. But underneath that shiny glass screen is this massive, chaotic, and honestly incredibly fragile physical architecture. And today, our mission is to sort of shortcut your path to understanding exactly how that hidden machine works.
And, well, why the line between everyday coding and high-level academic theory is completely blurring right now.
Yes. So welcome to another deep dive.
Glad to be here. You know, that illusion of perfection you mentioned, it is arguably the greatest magic trick of the modern era.
Oh, for sure.
We are relying on systems of just unimaginable scale. And the fundamental theme we're exploring today is how those systems are actually built entirely on trade-offs.
Because it's not just about tech, right? It's about trust.
Exactly. The infrastructure you use every day is all about trust and ultimately how much risk we are willing to accept in our digital lives.
Which brings us to our source material for this deep dive. It's a really fascinating interview from the Pragmatic Engineer channel. They sat down with Martin Kleppmann. And if you're in the tech space, I mean, you know the name.
Oh, absolutely. He wrote Designing Data-Intensive Applications.
Right, which is basically the generation-defining text on how to build back-end systems.
Yeah, it's the Bible for that stuff. But to really grasp where the internet is right now and why these complex architectural decisions matter, we have to rewind a bit.
Okay, let's rewind.
We need to look at the sheer pain of building the web a decade ago.
Right, because Kleppmann didn't just, wake up in an ivory tower one day and write an academic textbook. He started in the trenches.
He really did.
Back around 2008, he launched a bootstrap startup called Go Test It. It was this cross-browser testing service.
No, man, the dark ages of web dev.
Seriously. Anyone building websites back then remembers the absolute nightmare of making a single page look identical on Internet Explorer, Firefox, and Chrome.
Yeah, and people liked his concept, but the reality was that nobody wanted to actually integrate it or, pay for it.
Which is a slight problem for a business.
Just a bit. So the business model didn't pan out. But that failure led him directly to his next venture, which was a company called Rapportive.
Oh, I remember Rapportive. It was like this browser extension that pulled social profiles straight into Gmail.
Yep, that's the one.
You'd open an email from someone, and bam, their LinkedIn title, their recent tweets, their photo, it all just populated right there on the sidebar.
And it blew up. I mean, they went through Y Combinator, moved from the UK over to San Francisco, and eventually in 2012, they were actually acquired by LinkedIn.
Which is where Kleppmann's real baptism by fire happens, right?
Exactly. At Rapportive, he had this small team of 5 people running a fairly standard Postgres database. But suddenly, he is thrust into the belly of the beast at LinkedIn.
A whole different universe.
Dealing with massive, unprecedented scale. He's hand-coding MapReduce jobs in Java, and he starts working on this brand new open-source technology that LinkedIn had just built called Apache Kafka.
So Kafka is one of those terms you hear constantly in tech, but it rarely gets explained well. To understand it, think of a court stenographer.
Okay, I like this.
In a courtroom, a stenographer just types everything that is said chronologically, line by line. They don't go back and edit out a witness's statement if the judge objects.
Right, they just append.
Exactly. They just add a new line saying, objection sustained. That is essentially what Kafka is, a universal append-only log.
That is a brilliant way to conceptualize it, because at LinkedIn's scale, the problem wasn't just storing a lot of data. The real nightmare was integrating it.
Because they had, dozens of different systems?
Hundreds. You had user activity events, separate databases, machine learning clusters, data warehouses. They were all speaking different languages, and they all needed to share data instantly.
So instead of trying to wire every single system to every other system, which would look like a giant bowl of spaghetti, they just had everything talk to the stenographer.
Exactly. Kafka created this continuous, durable stream of data. Any system could publish a new event to the end of the log, and then any other system could read from that log at its own pace.
So the sales dashboard could be reading events from yesterday, while the security system is reading events from 1 millisecond ago.
And they never block each other. It totally decoupled the entire architecture. Kleppmann saw this paradigm shift and realized that to build these massive systems, engineers really needed to understand these foundational concepts,
So he essentially took a sabbatical to write them down, so the rest of us wouldn't have to learn the hard way.
which became the first edition of his book.
Right. But here's where the story shifts. Because the foundations of data systems have transformed drastically since he wrote that first edition. We are moving away from the physical reality of servers to the highly abstract realm of the cloud.
Yeah, Kleppmann points out that he had to release a second edition simply because the baseline assumptions of engineering had completely changed.
How so? Like,
Weird.
what was the baseline before?
Well, in the first edition, the basic assumption was physical hardware. You run a database on a machine, and it writes its data to a physical local disk plugged directly into that machine.
Makes sense.
And if you want to replicate data for safety, the database software has to talk to another database on another physical machine, which then writes to its own local disk.
But the second edition is all about cloud-native architectures. Now, people are building databases on top of object stores like Amazon S3.
Right, and the replication. It's not happening at the database level anymore. The cloud provider's object store just handles it invisibly.
Which leads to this massive debate in the industry right now. If cloud providers handle the replication, the uptime, the storage allocation, are engineers losing their fundamental skills?
There is a really great comparison here to memory management in programming.
Oh, lay it on me.
Decades ago, if you wrote code in C or C++E, you had to manually allocate and deallocate memory in the computer's RAM.
And if you messed up?
You got a memory leak and the whole program crashed. But modern programming languages use a mechanism called garbage collection.
Yeah.
The language automatically scans for memory you are no longer using and just frees it up behind the scenes.
So the coder doesn't even have to think about it.
Exactly.
And the cloud is essentially doing that for hardware infrastructure. But wait, let me push back on this a bit.
Go for it.
If we abstract everything away and we just blindly trust Amazon or Google to handle the hard stuff, aren't we driving blind? What happens when the check engine light comes on, the database grinds to a halt, and literally no one on the team knows how the engine actually works?
Well, that is the ultimate trap of abstractions. Kleppmann argues that you don't necessarily need to know how to build the engine from scratch, but understanding its internals remains a superpower.
So you still need the theory.
Absolutely. You still need to know, for instance, the difference between row-oriented and column-oriented storage, or how a log-structured merge tree operates.
Okay, let's demystify those because those terms sound incredibly intimidating.
They do, yeah.
Let's start with row versus column storage. What does that actually mean for the person trying to run a business?
Think of a massive corporate directory. A row-oriented database stores all the information about one person together. So name, address, phone number, salary, department.
Like reading left to right on a spreadsheet.
Exactly. If you are a bank looking up a single customer's profile, row storage is incredibly fast.
But let's say you want to run analytics. Like you want to find the average salary of every single employee in the company.
Right, and a row database has to load every single entire profile into memory just to read that one salary field. It completely chokes the system.
So a column-oriented database separates all the data by category. It stores all the names together, all the salaries together.
Yep. So when you ask for the average salary, it just rips down that one single column lightning fast.
That makes total sense.
And if you don't know how that works under the hood and you try to run heavy analytics on a row-oriented database, your system will stall, your latency will spike, and your cloud bill will just explode.
And you'll have no idea why.
Exactly.
Great.
It's the same with a log-structured merge tree, or LSM tree.
Break that one down for us. What's an LSM tree?
Traditionally, updating a database means the system has to physically find the specific location of that record on the hard drive and overwrite it.
Okay.
When you have millions of updates a second, the disk is spinning wildly, doing random writes all over the place, which is incredibly slow. An LSM tree works differently. It takes all the incoming updates and just holds them in memory.
Oh, it doesn't write to the disk immediately.
No, it just batches them up.
Right.
And when that memory buffer gets full, it flushes the entire batch to the hard drive in one massive sequential block.
Wow.
It turns millions of tiny, slow, random disk writes into one giant lightning-fast sequential write.
So understanding that mechanism lets you manage the ultimate trade-off, which is cost versus performance.
Precisely.
Which bridges perfectly to the next reality check. Because trusting the cloud doesn't just mean trusting their software abstractions, right?
Yeah.
It means trusting their actual physical infrastructure.
Yeah, we are transitioning from technical bugs to real-world chaos here. Kleppmann has a chapter called The Troubles with Distributed Systems that honestly reads like a sci-fi horror story.
It really does. It highlights the gap between theory and reality. In theoretical computer science, you might assume a message sent over a network will arrive in a predictable amount of time.
But in reality, networks are deeply unpredictable. A message might arrive in 100 microseconds, or it might get trapped in a routing loop and arrive 10 years later.
And how does a system even handle a command that arrives a decade late? It might try to execute a trade on a stock that doesn't exist anymore, or delete an account that was already recreated.
It's chaos.
But beyond just network routing, the physical vulnerabilities are wild. We tend to think of the internet as this ethereal, invisible cloud, but it's deeply physical. I mean, we used to literally have problems with sharks biting undersea internet cables.
Yeah, they were apparently drawn to the electromagnetic fields of the data flowing through them.
And telecom companies spent an absolute fortune wrapping those underwater cables in Kevlar and steel shielding just to stop the sharks.
But the funny thing is, as soon as the underwater problem was solved, the vulnerability just moved onto land.
Right. Today, one of the biggest unpredictable threats to terrestrial cables is actually cows.
Cows.
Actual farm animals. They wander over buried cables that has surface slightly, step on them, and cause massive network outages.
It's a brilliant, if totally absurd, illustration of why you cannot design a distributed system assuming perfection.
Right, because a server node going down isn't always a complex software crash.
Sometimes it's a power cord being tripped over by a janitor, or a literal cow in a field. This is exactly why companies move toward multi-region and multi-cloud setups.
But building a system that instantly fails over from, say, an Amazon data center in Virginia to a Google data center in Europe is incredibly expensive. You're essentially paying to run everything twice.
System design is ultimately a business decision about risk tolerance. Are you willing to accept a few hours of downtime a year, or is your service so critical, say, a hospital network or a payment processor, that you will pay double the infrastructure costs just to mitigate the risk of a regional outage?
And it's not just cows and power outages either. The source material highlights this from a European perspective, pointing out the geopolitical risk of being completely dependent on U.S. cloud services.
Right. If international relations deteriorate, or there is a major diplomatic breakdown, a whole region could suddenly be locked out of foreign cloud infrastructure.
And to be clear, we're just reporting the source's observation neutrally here, but it makes sense as an objective business risk. Centralization carries a single point of failure.
Whether that failure is a technical glitch, a farm animal, or a diplomatic crisis, the result is exactly the same. For highly critical systems, engineering a multi-cloud setup isn't just about technical uptime, it is a direct hedge against real-world geopolitical shifts.
Okay, so we've got physical risks, political risks, severe cost trade-offs. But as if that wasn't enough to worry about, the fundamental way we write the code running these systems is changing.
Big time.
We are entering the AI era, essentially handing the keys over to large language models. This brings us to vibe coding and why we are suddenly desperate for mathematical truth.
This is a major update in Kleppmann's current thinking. Technologies that defined the big data boom, like MapReduce, are effectively legacy systems now.
So what's replacing them?
The new foundational layers are things like vector indexes and data frames, which have surged specifically to support artificial intelligence.
Let's quickly clarify those. A standard database searches for keywords, right? If you type dog, it looks for the word DOG.
Simple enough.
But a vector index converts complex data, like images, audio, or entire paragraphs, into a mathematical map of numbers.
So if you search for dog,
It mathematically understands the concept of a canine. It might return a picture of a wolf, even if the word dog isn't anywhere in the file.
and data frames are basically massive programmable spreadsheets that feed those vector indexes directly into machine learning models.
But the real shift isn't just what AI is processing, it's what AI is building. We are seeing the rise of LLM-generated code.
Yes, large language models are now spitting out massive chunks of back-end architecture.
Which has led to this phenomenon called vibe coding.
I love that term.
An engineer asks an AI to build a function, the AI generates it, the engineer looks at it, runs a couple of basic tests and says, yeah, the vibe feels right, and just pushes it to production.
Which is terrifying when you are building critical infrastructure.
Oh, absolutely.
AI models are prone to hallucination. If an AI agent creates subtle tangles in the logic, or duplicates functions unnecessarily, it turns your system architecture into a big ball of mud.
And over time, the structural integrity of the entire system degrades.
Plus, we cannot manually review all this AI-generated code. Human engineers would instantly become the bottleneck.
So how do we verify code if humans can't read it fast enough? Kleppmann suggests we need a fundamental shift from traditional software testing to formal verification.
Now, that's a huge shift.
Right, and I want to make sure we nail this distinction. Today, the way we test code is by checking edge cases. You write a program to calculate discounts, and you test it by inputting a 0. Does it crash? No. Then you input a million. Does it crash?
It relies entirely on the human engineer being creative enough to think of every possible scenario that might break the system.
But formal verification isn't just testing examples.
Not at all. It's using pure mathematics to prove, beyond a shadow of a doubt, that the logic holds up across an infinite number of variables. You are literally proving a mathematical equation across an infinite state space.
How do you even do that?
You use highly specialized proof assistant languages like Isabelle or Lean. And these aren't programming languages like Python or Java that you use to build a user interface. They are essentially logic compilers.
So you write out the mathematical rules of your system.
Right, and the compiler verifies if your algorithm will always invariably satisfy those rules without any contradiction. Because if a bug could corrupt millions of records, checking a few examples just isn't enough. You need absolute, unassailable truth.
But Kleppmann admits he never used formal verification when he worked in startups. Why? Because it is agonizingly slow. It can take months of a highly specialized engineer's time to mathematically prove a single algorithm correct.
Which brings us to one of the most fascinating paradoxes in modern tech.
Lay it on us.
AI is creating this massive influx of vibe-coded software, which drastically increases our need for formal verification because we can't trust the code.
Yeah.
But at the same time, AI might be the exact tool that saves us.
Wait, you mean the AI writes the proof?
Exactly. LLMs are getting surprisingly good at writing these laborious mathematical proofs. The very technology that is generating the untrusted code could democratize the ability to formally verify it.
Wow.
It could take formal verification out of the slow-moving world of academia and make it a standard automated tool in everyday industry.
That is a wild feedback loop.
Yeah.
AI writes the code, and then AI does the complex math to prove to us that the code won't destroy the system.
It really is.
And that actually brings up a bigger issue with centralization, because relying on massive cloud providers and giant AI models has triggered a huge counter-movement. And this rebellion is largely happening in the academic world.
The conversation in the source turns heavily toward the ethics of engineering here.
Yeah, there is a growing realization that technology is not neutral. For a long time, engineers focused purely on building technically impressive products, often ignoring the societal consequences.
Like building massive data harvesting machines optimized solely for engagement.
Right. Kleppmann argues that engineers have a fundamental responsibility to articulate these societal risks to business leaders.
And one of the most tangible ways he is pushing back is through a concept called local-first software.
Right now, we live in a SaaS world. Software as a service. You use web-based document editors or design tools, and your data lives entirely on their servers.
Kleppmann says these companies effectively hold a gun to the customer's head.
You pay your monthly subscription, or you lose access to your own work.
Local-first software flips that dynamic entirely. The idea is that the software and the data should live primarily on your local device.
You can still sync with the cloud for collaboration, right?
Sure, but you aren't dependent on it. If the cloud provider goes out of business, or you cancel your subscription, or you are just on an airplane without Wi-Fi, your files are still fully functional and yours to keep.
That sounds great for you, the user, but building it is a massive engineering headache. Let's look at a concrete example, document access control.
This is a tricky one.
Let's say you and I are collaborating on a local first document. I decide I don't want you involved anymore, so I revoke your edit access. But right at that exact millisecond, you go offline and you make a bunch of edits to the document on your laptop.
Now, in a centralized cloud system, that conflict is super easy to resolve. The central server is the single source of truth.
It receives my revocation, it looks at the timestamps, and when you finally reconnect, it just rejects your offline edits.
But in a decentralized local-first system, there is no central server.
Right, and you might say, well, just trust the clock on the devices. But you can't.
Definitely not.
If you are a malicious user who just got fired, you could simply backdate the clock on your laptop to make it look like you made those edits before I revoke your access.
Trusting device timestamps in a distributed system is a massive security vulnerability.
So how do you resolve an edit and a revocation happening simultaneously across offline devices without a central authority?
It requires a novel mechanism called conflict-free replicated data types, or CRDTs.
Break down how a CRDT actually works.
A CRDT doesn't care about clocks at all. It tracks the logical mathematical relationship between edits.
Okay.
If an edit to change text and an edit to revoke access happen concurrently, the CRDT merges them based on absolute rules built into the data structure itself.
Like establishing a rule that revocations always trump edits.
Exactly. It uses causality rather than time, ensuring that when our devices finally sync back up, they mathematically guarantee the exact same end state without needing a server to arbitrate anything.
But if this is so vital for user autonomy, why aren't the big tech startups solving it?
Because startups are heavily incentivized to take the easy route. A centralized server is much easier to build, and it guarantees recurring subscription revenue.
And academia.
Academia has the long-term freedom to tackle the harder, less profitable engineering problems. They can afford to spend years solving decentralized access control because their goal is protecting user autonomy, not meeting quarterly revenue targets.
So they're building the unglamorous infrastructure so that down the line, someone else can build a profitable, ethical alternative to the sauce trap.
Precisely. And this academic freedom extends beyond just software, too. Kleppmann is also researching how to use cryptography to verify things in the physical world.
This is such a fascinating application. For instance, the European Union has new regulations preventing the import of products tied to deforestation, things like coffee, cocoa, and palm oil.
The importer actually has to prove exactly which plot of land the beans came from, cross-referencing it with satellite imagery to prove trees weren't cut down. But here is the catch for the business. If I'm a massive coffee brand, I do not want to publicly reveal my exact supply chain to a central regulator. That's my secret recipe.
Right.
I don't want my competitors knowing which specific farms produce my best beans.
Traditionally, those conflicting incentives lead to creative accounting and greenwashing. Companies obscure the truth to protect their trade secrets. But Kleppmann is researching how to use a mechanism called zero-knowledge proofs to solve this.
I love the concept of a zero-knowledge proof. It's like having a giant Where's Waldo puzzle.
That's a great analogy.
You want to prove to me that you found Waldo, but you don't want to show me where he is on the map. So you cover the entire puzzle with a massive piece of cardboard that has one tiny hole cut out.
Right.
You place the hole directly over Waldo. I can see Waldo through the hole, so I have mathematical proof that you found him, but I have zero knowledge of where he actually is on the page.
That is exactly the mechanism. Applying that to the supply chain, a company can cryptographically process their supplier data and hand the regulator a mathematical proof, and the regulator can verify it.
With absolute certainty. They can prove the supply chain is clean and deforestation-free, without ever seeing the sensitive data about who the actual suppliers are.
So instead of trusting a corporate PR campaign, the claim is backed by unhackable math. It is a profound shift in how we establish trust.
It is removing human fallibility from the equation entirely.
Okay, let's take a breath and recap the incredible journey we just went on. We started with the scrappy days of cross-browser testing, moving into the big data revolution where Kafka became the universal stenographer of the internet.
We explored the double-edged sword of cloud abstractions, where engineers no longer have to manage physical memory but risk flying blind if they don't understand internal mechanisms like column storage and LSM trees.
We saw how distributed systems are vulnerable to everything from unpredictable network delays to literal cows stepping on cables, forcing massive investments in multi-cloud architecture.
And then we hit the AI era.
The wild west of vibe coding.
And the absolute necessity of using infinite state spaces and formal mathematical proofs to ensure our infrastructure doesn't just collapse.
Finally, we looked at how academia is fighting back against centralization, using CRDTs to build local-first software so you actually own your data, and using zero-knowledge proofs to verify physical supply chains.
All of which leaves us with a rather profound question to consider.
What's that?
Well, if the future of technology is moving inextricably toward mathematical proofs, whether it's formally verifying AI-generated code or cryptographically proving a company's carbon footprint, how will our society adapt when trust is no longer placed in institutions, brand names, or even human judgment, but entirely in equations?
That is a very heavy thought to chew on. So next time you click a button and expect magic, remember the cows, the complex math, and the invisible architecture making it all happen.
Thanks for joining us on this deep dive, and keep questioning the systems around you.